Now, solubility and intermolecular forces. Water molecules are polar. So, molecules such as water have charges separated into positive and negative regions. They are considered to have a permanent dipole. So what we have here, we have the oxygen that is slightly negative, right? If we look at the electronegativity as we've looked at in previous chapters, so oxygen is going to carry a slight negative charge. The hydrogens are going to carry a slight positive charge, and there is that force of attraction there, that hydrogen bond that actually forms between molecules of water, and that's what makes water molecules have the properties that they have. Think about when you're filling up a glass of water, that, and you can try this at home. It's a really safe experiment. Try to fill up water to the brim, or and then try to add just drops, and you'll see that you'll be able to fill water up just slightly above the brim, because water has that cohesion, right? Because the hydrogen molecule the hydrogen of one molecule of water is attracted to the oxygen of another, and eventually it's gravity that kind of kicks in and causes maybe that to overflow beyond it. Right? But you do have that ability to allow for the water to actually go above the brim. A dipole consists of two opposite charges that are separated by a short distance. And that short distance here, as formed by the hydrogen bond that kind of separates, that keeps them together but still has that separation. It separates each molecule of water from one another. A dipole-dipole attraction. Dipole-dipole attractions are attractions between opposite charges on two different polar molecules. Right? So we're looking at two completely different polar molecules that are attracted. With the example we showed you before, it was one molecule of water with another water molecule. Okay? They're both the same type of polar molecule. But here, a dipole-dipole attraction is that of one polar compound with another polar compound. These attractions are considered intermolecular. Okay, so if the force is greater between two different dipoles than between the dipoles on the same molecule, then the solute will dissolve in the solvent. Then we have here an ion-dipole attraction. The positive end of a polar molecule attracts the anion. The negative end of the dipole attracts the cation. So what we're looking at is something like salt dissolving in water. Right? So we have Na, which is positively charged, Cl, which is negatively charged. And we talked about the dipole attraction within water, and how water, right, oxygen is slightly negative, hydrogen is slightly positive. So there's going to be this attraction between the oxygen molecule of the water with the Na of the salt. Right? So then we have the Cl, which is negatively charged, which means it will be attracted to the slightly positive hydrogens of a water molecule. Right? So opposites attract. Right? So this H, which is slightly positive, this chlorine, which is slightly negative, there's going to be an attraction that occurs between these two. Right? That's why the oxygen is going to be completely away from the chlorine, because the oxygen is slightly negative, chlorine being negative, right? They're like charges. They will repel one another, so it will kind of rearrange the water molecule in a way where it'll allow the hydrogens of the water molecule to surround the chlorine, while with sodium, it'll allow the oxygen molecules to surround the sodium. Sorry for writing over some of the text. Okay, so notice here with the Na part of the NaCl, all the oxygens which are slightly negative are going to be attracted to the each one of the sodium ions. So, ionic compounds will dissolve in polar solvents. So, sodium chloride, being ionic compound, will dissolve in something that is polar, being the water. Hydration of ions. We've talked about hydrates, the dot, the H2O at the end, okay? So when water molecules completely surround an ion. So what we have here is we've got our anion, and as we just showed you, right? So imagine this being the chlorine part, right? The Cl being negatively charged, and notice how it's the hydrogens that are pointed in the direction of the anion. Sorry, I used red. I should have used something like blue here. Okay, this is the chlorine, right? So let's look at, so we've got that. And so here, let's look at this one again. Cl, chlorine being in the middle. Notice what's pointed in the direction of the negatively charged chlorine, right? So it's the slightly positive charge of water. On the other end, we have the cation. So this was, let's say, the sodium, right? Sodium is positively charged. Notice what part is pointed in the direction of the cation, right? Being the sodium ion, all right? It's the part of the oxygen which is slightly negative, according to electronegativity. An electrolyte is a solution that can conduct electricity. Not all ionic compounds are soluble in water because the force of attraction within ionic compounds are too strong. An example of that would be silver chloride. Is one to remember, one example to remember.